Okay, so might have to do this one in parts because it's kind of long. This is, oh, it got cut off. This is 2014 Mechanics 2. It's for group 2.9. Let's see. So basically, let's highlight the important part. A small block of mass M starts from rest at the top of a frictionless ramp. All right, we see that, and then I see that I'm looking at the top view. And it looks like that's your mass, so I'm just gonna make some conclusions here. That we're gonna be looking at this as what happens on the ramp. So I would guess I would say like ramp section of the problem. And whatever this is, circle section, track, rough wall section of the problem. So it's always important just to even kind of get that idea from your pictures. All right, so a block of mass M starts at the top of a frictionless ramp. Seems important, frictionless right there, with a height of h above a horizontal tabletop, as shown above in the side view. Block slides down the, again, they're telling you, smooth ramp and reaches point P with a speed of v naught. The fact that they say speed right there kind of makes me think that this is going to have something to do with conservation of energy and have kinetic energy involved. Okay, so then it says after the block reaches point P at the bottom of the ramp. Okay, so now we're going to switch views to the top view. It slides on the tabletop guided by a circular vertical wall with radius r. Okay, that's the wall, we see that. The tabletop has negligible friction. Okay, so this part of the table is slick. Okay, it's like ice, that's how I think of it. And the coefficient of kinetic friction, okay, hang on, between the block and the circular wall. So what that is that's right here. That's your wall. So imagine this wall is like rough on the inside. All right, that is mu. So my rough surface went away, but we're just saying it's rough on the inside of the wall. All right, so mu. So let's go ahead and look at this. A, derive an expression for the height of the ramp h. Express your answers in terms of v naught and m. Make sure you know to do that. And any fundamental constants is appropriate. In mechanics, that's pretty much g for this kind of problem. So in A, let's look. Well, since this is like so perfect and awesome right here, and that's, you know, frictionless, that's a pretty straightforward conservation of mechanical energy problem. Do not let the simplicity of this like trip you up. Remember, their goal is to get you to waste time questioning your sanity. So mechanical energy equals mechanical energy prime. You start off with just potential energy due to gravity, and you're going to end up with kinetic energy. 1/2 mass, that's an m. Speed, or v naught squared is what they said. Oh, my neighbor's dogs are being so annoying. And hopefully you know how to solve this. So therefore, height equals v naught squared over 2g. There you go. So that's A. All right, now this is where it gets a little bit weird. Okay, you got it. This is where you really have to read the question. After a short time passing point P, the block is in contact with the wall. So now we're over here in this blue section and moves with a speed of v. We got a new factor in here. So look at this very carefully. B, part 1, is the vertical component of the net force on the block, upward, downward, or 0. This is a dirty trick. It is on the very smooth table, as it has indicated. Now, the block is in contact with this rough wall. This is kind of a side view cutaway that I'm doing. But let's just look at what's happening to the block. Here's your block. Okay, and this is, let's say I just kind of did a cutaway like right about here. Okay, just kind of cut the table. This is your side view. So you know that it's going to be accelerating this way because, you know, like you got R right here. It's going to be accelerating towards the center because it's, you know, the track is circular. Now let's look. We got the smooth tabletop, so whoops. So you have your weight, right? And you have your normal force that balances it out. Okay, so 0. Acceleration, I put vertical, is 0. Therefore, net force, I'm going to put vert. You can put y if you want. I just don't want to have to define my axis. Maybe put, just to cover myself, by Newton's second law. Yeah, I think think that's it. I put like AC there. I think that that's good enough. So that's that portion of it. So anyway, let's look at the second part. Okay, I brought this part over to this side just to have it. So now this is part 2. We're still looking at the blue part of this up here. On the figure below, draw an arrow starting on the block to indicate the direction of the horizontal component. Okay, notice they say arrow and horizontal component because I didn't notice that the first time I did it, of the net force moving on the block with the position shown. At this point, you're probably like, oh my God, how can that be? A free body diagram is the net force. Why are they asking me to do that? Isn't that asking like where on earth is Earth? It doesn't make sense. They're being tricky. Let me show you what I did, which would have gotten the 2 out of the 3 points. And actually, I think you can use it to justify, of course, because they ask justify your answer, as they tend to. So I'm going to draw a version of this over here, and I'm going to show you what I did. Here was my reasoning. So I started thinking about it. So I'm like, okay, well, I drew my acceleration way far away from the diagram. I know my acceleration is going this way, towards the center. Let's say the center is like right here. So what's causing it to accelerate? Well, it's got a wall pushing on it. It's on a slick table, but it's got a wall pushing on it. So we know that that is the normal force. Because, like, imagine that cutaway again. Okay, here's my block. See how the surface of this, it's supposed to be a rough surface, the surface of this block is 90 degrees. You wouldn't want to draw that 90 degrees thing there, but I just want to show you that's 90 degrees, that's normal force. You can have normal force pushing against you. So you got your normal force like that. But then I was like, hold up, it's kind of slowing down. Why? And I was like, well, there's friction. So if I were sliding on this with really loose, like, you know, clothing on, which way would my clothing get pulled? And it would be back if I'm looking at that exact moment. So your force of friction slowing this down, right? So that's what I put, but that's not what they wanted. They wanted, basically, you see how I have these two? I could move this over here, or I could move this down here, and that would give you your resultant. They just want the resultant because, frankly, this isn't a free body diagram, and they're being weird. It's like a cheap middle school bully trick. Okay, so I would do that, and do not label it because they didn't ask you to do that. They usually do. This is why they also ask you the question above it to prime you, to get you confused. So because then you're like, oh, I'll do X and Y. And if you labeled the other one like X and Y, it could get really confusing. That's why I put the vertical thing. Anyway, so you have this. For your justification, I would actually draw this for my justification. I'd be like, Fn causes mass to accelerate to the center. F, force of friction. Let's see, force of friction, X. Force of friction, let's see how to put this. Force of friction causes centripetal acceleration to decrease. That's what I would put. I think that's good enough for that. So I'm going to stop it right here and do a second part.